The next operator in our system is the arrow or horseshoe. Arrow sentences represent conditional statement. Now, we've talked about conditional statements before, only to say that one statement, one conditional statement, is not an argument. And at the same time, conditional statements can be parts of arguments. And indeed, conditional statements play an important role in all kinds of deductive arguments in particular. So let's start by saying that a sentence like A arrow P will represent a statement like, if you ace test 2, then you will pass the class. We're going to call this part the if part, where I say if you ace test 2, the antecedent of the conditional. And the next part, the part that says what will happen, then you will pass the class, is called the consequent. That's with a T. It's not consequence, although it sounds similar. There's a reason why it's something different from a consequence, which we'll get into later. And I want to proceed straight to the truth table for arrow sentences next. It's another binary operator, so as usual, we have to set up all the possible combinations of truth values for our input statements. And we have to define what do we want our output to be in each possible case. But again, we don't just decide to do this however we feel like. We want this to represent a statement like, if you ace test 2, then you'll pass the class. Now, I think the easiest way to decide how we should do this is to think about what would make this false. That is, if I said to you, if you ace test 2, then you will pass this class, what would make me a liar? And of all the cases that we've outlined, you should be able to see that it would make me a liar if you aced the test and then you didn't pass the class. I said that if you ace test 2, then you will pass the class, and that didn't happen. So we should define our output in that case to be false. Now let's think about some of the other cases. The first case, where you ace the test and then you do pass the class, well, that sounds just like what I said would happen. I said if you ace the test, then you will pass the class. So we ought to define that output as true. Similarly, on the last row, where both statements are false, I said if you ace test 2, then you will pass the class. You don't ace test 2, and then you don't pass the class. Well, I didn't say you'll pass the class if you didn't ace test 2. I only said if you did. So I didn't say something false there. And since the two possibilities are true and false, we should define our output there as true. Now, the third possibility we listed, that you do not ace the test, but you do pass the class anyway, may give us some pause here. I said if you ace test 2, then you will pass the class. Let me ask you this. What did I say would happen if you didn't ace test 2? Did I say that you will not pass the class if you do not ace test 2? I didn't actually say that, did I? I said if you ace test 2, then you will pass the class. If you do not ace test 2, I didn't say anything about what would happen. Maybe it's possible that you could still pass the class in some other way. Maybe you could ace the third test. Or maybe you could hack into the system and change your grade. There may be other ways that you could pass the class without acing test 2, and it's still true, as I said, that if you ace test 2, then you will pass the class. So we'll define our output as true there. Now, when we look at our completed truth table, we find that we can express the rule verbally in this way. A conditional statement is only false when the antecedent, now that's on the left in symbolic logic, is true, and the consequent, which is on the right side in the symbolic version, is false. That is, both those two conditions have to be met. The left side must be true, and the right side must be false. So this is the first operator, and I'll just tell you the only operator, that we're dealing with, where the order matters. It has to be true on the left and false on the right, and then it's false, not the other way around. So one thing you may notice about this, there are two cases where the left side, the antecedent, is false. In both of those cases, the conditional itself as a whole becomes true. You can also notice that there are two cases when the right side, the consequent, is true. And in both of those cases, the conditional as a whole is true. So a true consequent will always make the conditional true, and a false antecedent will always make the conditional true. In order to keep this in mind, it might be helpful to make note of certain statements that flaunt or abuse that fact about conditional statements. So, for example, suppose I know that the consequence of a conditional statement is going to be true. I can put whatever I want in the antecedent and know that I'm going to be saying something true. So, for example, I say to my roommate, if you do the dishes, I'll cook. And now my roommate thinks, oh, this is a great reason to do the dishes, right? Because if I do the dishes, he'll cook. But what if I'm planning on cooking anyway? Then it's also true that if you don't do the dishes, I'll cook. If you don't do the dishes, I'll still cook. Now, since I already know the consequent of my statement is going to be true, I'm planning on cooking anyway. It doesn't mean that I lied when I made the first statement. It's true. If you do the dishes, I'll cook. I really will. It's just I didn't mention that if you don't do the dishes, then I'll cook. And then we have expressions like expressions about eating my hat and so on. These sort of flaunt the fact that a false antecedent would make any conditional statement true. So I make the statement that I will eat my hat if, and then it's something that I know is going to be false. Like I say, if you learn to translate Latin into Japanese, then I will eat my hat. And I know that the antecedent of that's going to be false, because you're not going to translate Latin into Japanese. So I won't have to eat my hat, but my statement will be true. So now that we've explored the logic of the conditional statement, the truth condition of the conditional statement, we see that it's a little bit tricky, but I'm sorry to tell you things get a little bit worse too. Because English has all kinds of ways of stating these conditional statements, and they're awful. And they create a lot of confusion. Now we want to take a look at this. Sorting out confusion is our job here. So I'm sorry if this is confusing, but conditional statements just are that way. And we have to sort it out. So we've looked at a statement like, if you ace the test, then you pass the class. And we're representing that with a arrow or horseshoe, P. Some other ways that you could state this are pretty simple, easy to see. I could say, if you ace the test, you pass the class. All I did is leave out the word then. We're allowed to do that. I can also put the part with the if on the end of my sentence. I can say, you pass the class if you ace the test. there's something pretty significant to notice here. In our symbolic system, what signifies antecedent versus consequent is direction. The antecedent's on the left side of the horseshoe. The consequent is on the right side of the horseshoe. In ordinary language like English, this is not indicated by direction. This is not indicated by where things appear in the sentence. Instead, it's indicated by being linked up with the word if. So, if you ace the test, doesn't matter if it comes at the beginning of the sentence or at the end of the sentence, it's still the antecedent of the conditional. So that is also a horseshoe P. Another way of putting conditional statements is in terms of stating it as a condition. So I might say that acing the test is a sufficient condition for passing the class, or even just that acing the test is sufficient for passing the class. Sufficient means enough. It gets you there. So saying acing the test is sufficient for passing the class means if you ace the test, then you pass the class. Now let me draw your attention to another kind of statement about conditions. And suppose I say that acing the test is a necessary condition for passing the class. So I didn't say sufficient condition, I said necessary condition. First question, would that be the same as saying that it's a sufficient condition? Hopefully you can see that that's not the same as saying it's a sufficient condition. If I tell you acing the test is a sufficient condition for passing the class, well then that's good news. All you gotta do is ace the test and you pass the class. By the way, one thing we notice when we're exploring the logic of conditionals is that it doesn't mean you have to ace the test. If I say that acing the test is sufficient for passing the class, if you ace the test, then you pass the class. But that doesn't mean it's the only way you can pass the class. Now if I say acing the test is necessary for passing the class, that's not good news, that's bad news, right? That means that you have to ace the test in order to pass the class. So clearly this is not the same as the statements on the left, so this cannot be a horseshoe P. Consider another type of conditional statement. Suppose I say you pass the class only if you ace the test. Now this seems to be the same as saying it's necessary, right? It's the only way you can pass, is if you ace that test. Only if you ace that test can you pass. So we have two statements on the right here that are not the same as what we've done on the left. They're not the same as this A horseshoe P statement. So how are we supposed to represent them? Well, consider this for a second. Remember what we said about the truth conditions of the statements on the left. They're all A horseshoe P, which means, according to our definition of a horseshoe or arrow, the only case where these sentences is false is when A is true, and at the same time, P is false, when the antecedent is true and the consequence is false. That is, in the case where you ace the test but you don't pass the class, that's the only thing that makes those false. Consider the question, what would make me a liar if I gave you one of the statements on the right? If I said acing the test is necessary for passing the class, or I say you'll pass the class only if you ace the test, and we look at all the possible truth values for A and P, what would make it a lie when I said acing the test was necessary for passing the class? Well, if you don't ace the test, then you pass the class anyway. Wouldn't that mean it was false? It wasn't necessary. So this assignment, where A is false and P is true, our statements on the right are false. But if it turns out you don't ace the test and you don't pass the class, well, then that sounds a lot like what I said would happen. I said acing the test was necessary for passing the class. And meanwhile, if you do ace the test and then you pass the class, well, then I didn't say you wouldn't. I said acing the test was necessary, and that is something that you did. So the values at the bottom and top of our table ought to be true for our statements on the right. And then we have the second possibility where you do in fact ace the test, but you don't pass the class. Well, did I say that if you ace the test you would pass the class? No, I didn't. I said acing the test was necessary for passing the class. That doesn't mean that it's sufficient. That doesn't mean it's all you have to do. There could very well be other things that you need to do in order to pass the class that I just didn't happen to mention. I said acing the test is necessary, but maybe that's one necessary condition among many. Maybe you'll also be required to attend every class meeting. Or maybe you'll have to learn to translate Latin into Japanese in order to pass the class. I didn't say that any of these things were not necessary. I only said that acing the test was necessary. So our statements on the right ought to be true in that case as well. If you still find this a little counterintuitive, let me give you an example of a more familiar necessary condition. Let's say you're at Cedar Point and you're waiting in line to get on the roller coaster. When you get to the front of the line, you see a sign that says you have to be over this height, it's usually about 4 feet tall, in order to ride the roller coaster. Now it seems clear that that's giving you a necessary condition for getting on the roller coaster. So we could say being over 4 feet tall is a necessary condition to ride the roller coaster. You could also say, as we saw, you can ride the roller coaster only if you're over 4 feet tall. Now let's say your friend Jane gets to the front of the line and Jane is over 4 feet tall. Does that mean she gets to ride the roller coaster? No, it does not. It does not mean necessarily that she gets to ride the roller coaster. The sign stated a condition that it was necessary to be over 4 feet tall. But in fact, there are other conditions as well. Being tall enough is just one requirement, and there may be other requirements. It's also a necessary condition to ride the roller coaster that you not be pregnant. So you can ride the roller coaster only if you're over 4 feet tall, but also you can ride the roller coaster only if you're not pregnant. So just being 4 feet tall doesn't get you necessarily on that roller coaster. Now let's go back to comparing different ways of stating conditional statements. Now we know how to represent the statements on the left, but we're not sure about the statements on the right. When I say acing the test is necessary for passing the class, we did decide that if you pass the class without acing the test, then that makes the statement false. And in these other cases, the statement is true. Now do you notice a similarity between the truth table that we've just constructed and the truth table for the arrow or horseshoe on the left? The horseshoe was only false when the left side of it was true and the right side of it was false. And now we're talking about a statement, the way we have our letters arranged, which is only false when the right side is true and the left side is false. So maybe we should have sort of a backwards arrow to represent that? Actually, no, I have a better idea. If we just list A and P in the other direction, then look what happens. The assignment where P is true and A is false now is the second assignment. because we simply switched the order on those two. So now our table looks just exactly like the table for the horseshoe or arrow. So all we have to do to represent the statements on the right is we can use the arrow and just flip the order so that we have P arrow A representing the statements on the right. And the statements on the left are A arrow P. In other words, this sort of directional relationship has been reversed. Now, this is really easy to keep track of in a symbolic language like this. If the arrow points from A to P, that's one thing, but if it's pointing from P to A, that's a different thing. In English, it's a bit rougher, but here's how we can keep track of this. Remember that a necessary condition is a consequent. And similarly, an only if clause, where it says only if you ace the test, only if also signifies a consequent. Meanwhile, the phrase a sufficient condition is an antecedent, and it's indicated by the word if, connection with the word if. So if you ace the test makes that the antecedent, but only if you ace the test. That's totally different. That makes that the consequent. So keep things straight in terms of those key phrases. So now we've said that A horseshoe P can be expressed in any of these ways, and meanwhile P horseshoe A can be expressed in any of these ways. But if you think about what I just said, then I should be able to express P horseshoe A by using the if phrase, since P is an antecedent. Something kind of weird happens if I try to do that. If I say passing the class is sufficient for acing the test, that sounds incredibly strange. Passing the class is sufficient for acing the test? And if I try to use any of the other expressions on the left to express the arrow statement on the right, it sounds similarly strange. If I say, if you pass the class, then you ace the test, that sounds bizarre. The same thing happens if I try to express A horseshoe P using the English expressions on the right. So if I try to say, you ace the test only if you pass the class, that sounds strange. And if I say passing the class is a necessary condition for acing the test, that also sounds incredibly bizarre. You can sort of understand these statements in a way if you just think carefully about the truth conditions that are involved. You ace the test only if you pass the class. That means the only way that you're going to ace that test is if you also end up passing the class, which is telling you that acing the test gets you past the class. It's a sufficient condition. You can imagine talking about a class that happened in the past and saying, like, having passed that class is a necessary condition for having aced that test. So just anybody who didn't pass that class, you know they must not have aced that test because that gets you past. And you could sort of understand these statements if you take time out of the equation. Our system doesn't really care about what time you find out things are true. The arrow or horseshoe only represents that the antecedent will not be true without the consequent being true. But maybe the English expresses more than that, or maybe it's just a rule about when you're supposed to say it a certain way. We could find other English conditionals where you could say it either way and it would sound perfectly fine. For example, if I say, if Dave goes to the party, then Eddie goes. The antecedent there is if Dave goes to the party, so that's D arrow E. Now, that's with the if-then construction. I can express this with only if just as easily, and it doesn't sound so strange. I could say, Dave goes to the party only if Eddie goes. Now, that's also D horseshoe E. A common mistake is to think that somehow you have to change something between these two statements, because one is if and the other is only if. But because the only if goes with only if Eddie goes, that's the consequent. And because the if goes with if Dave goes, that's the antecedent. So these two statements are the same either way. Now, I realize that if you hear the first statement, if Dave goes, then Eddie goes, it makes it sound like Eddie waits to find out if Dave's going to go or not or something. But it doesn't necessarily mean that. It could be that Dave carries Eddie around on his back everywhere he goes. So, if Dave goes to the party, then Eddie goes. And meanwhile, the second statement, Dave goes to the party only if Eddie goes. Well, that makes it sound like Dave waits to find out if Eddie's going to go, and then he doesn't go unless Eddie goes. But either way, the upshot in terms of what's going to be true and what's going to be false, both these statements mean that you won't find Dave at that party without Eddie at that party. And meanwhile, the opposite conditional E horseshoe D, you can also express either way. You can say if Eddie goes to the party, then Dave goes, or you can say Eddie goes to the party only if Dave goes, and both of those sound perfectly fine. Now let's play around a little bit with these statements of conditionals. And I want you to choose the correct word from the two in parentheses that makes the statement true. So in other words, if it's a blank, then it's a blank. Choose tiger or cat and make that true. Hopefully you got the right result that if it's a tiger, then it's a cat. Now try another one. It's a blank if it's a blank. This should say it's a cat if it's a tiger, because anything that's a tiger is going to be a cat, right? How about this one? We should have it's a tiger only if it's a cat. In order to be a tiger, it's got to be a cat, right? And the next one? It's being a tiger is sufficient for it to be a cat. It doesn't have to be a tiger to be a cat. But if it is a tiger, that makes it a cat. How about the next one? It's being a cat is necessary for it to be a tiger. It can't be a tiger without being a cat. All of these are ways of expressing the truth functional relationship T arrow C. So now the final result about conditionals is that any of these expressions need to be represented by P arrow Q. And the order matters here. We have if P then Q, or P only if Q. Now notice that's the same order as if P then Q. Q if P. That's the one where the order is reversed. Or we could say P is sufficient for Q, or we could say Q is necessary for P. Remember also that if you take any of these expressions and switch the Q and the P, you will then get the reverse Q arrow P. But expressions B and C are not the reverse of each other. It's if you reverse either one of those. And meanwhile, at the same time, bear in mind this difficulty about expressions like B and E versus the other ones, A, C, and D. Sometimes you're supposed to say it one way, sometimes you're supposed to say it another way, and sometimes it doesn't matter. So hopefully this gives you a better understanding of conditional statements. It's one of the toughest subjects that we're dealing with in our symbolic logic section here.